Hey there everyone. I have one more video for us this week, and this time we're going to attempt a problem that is significantly more challenging than anything that we've worked on so far, primarily because it involves a new topic, differential equations. I'll do my best to approach this one as carefully and concisely as possible, but please let me know in the comments if something wasn't clear or if you had any further questions. I'll try to respond as soon as I can and answer things to the best of my ability. Anyways, let's take a look at the free body diagram, sum of forces, and a useful expression that we'll need in order to complete part A. Here, I've represented our falling object by a circle. You can use a block or something else if you like. It really doesn't matter. What does matter is including a proper coordinate system. Notice that, unlike in the previous videos, our y-axis now has plus y pointing downward. Well, this is chosen because the object only falls in one direction, down. And this choice saves us a step from having to multiply things by -1 later. There's only two vectors influencing the object's motion here, the object's weight and the resisting force, kV. We can include a downward acceleration vector off to the side as well, and that's it. There's only three of them. Let's move on to the sum of forces next. Thankfully, there's not a whole lot for us to do here, because in the x direction, nothing is happening. There's no horizontal movement, so that sum is 0. In the y direction, we have just a single line, and that's it. Nothing else to do here either. Before, I mentioned requiring some useful expression before we start the derivation, though. That expression represents the terminal velocity for this particular fluid resistance, okay? This one, kV. Let's go ahead and grab that expression real quick. If you've seen the video for problem number 22 in this playlist, this approach may look pretty familiar. Here we have the sum of forces in the y direction on the left with our velocity variable exchanged with a new one, v sub t, where it represents the terminal velocity. And on the right, we've set the acceleration to 0, because once we hit terminal velocity, we don't accelerate anymore. Our speed doesn't change. Let's begin by exchanging the weight with mg first. Then we'll take the kv sub t term and move that over to the right-hand side. If we divide both sides by k, well, now we have what we were looking for. Keep this in mind as we proceed to the next page. Now it's time for the hard part, the derivation. Let's go back to our previous equation and change that velocity variable back to just regular v. Our first step is adjusting the right-hand side. Recall that the derivative of velocity with respect to time is the definition of acceleration. So let's incorporate that here. And here I've wrote dv over dt prime for an important reason that we'll cover in the next slide. We're just going to roll with that for now. Next, we will exchange the weight for mg, its definition, once again, and then next, divide both sides by k, like this. Do you notice anything familiar on the left-hand side, right there? Well, that's our buddy that we solved for earlier, the terminal velocity. Let's exchange mg over k for v sub t, like this. I'm going to bring that expression onto a fresh page and prepare our next step. Well, two steps together, in fact. We're going to divide both sides of the expression by m and multiply both sides by k. That way we'll end up with dv over dt prime isolated on the right-hand side. Here is where we're going to use a differential equations technique known as separation of variables. To put it simply, we want all the terms that involve v on the right-hand side to hang out with dv, and we want all the other junk on the left. To do that, we're going to break this derivative up. The starting point is to multiply both sides by dt prime. Okay, so now we have dt prime on the left. I can't divide this terminal velocity out from v because it's a difference, so I'm going to have to bring this whole thing over to the right-hand side. So let's divide both sides by everything in the parentheses here, and this is what our next step looks like. Everything is now considered separated, and at this point we can now integrate both sides with the appropriate limits, like this. On the left, k over m doesn't have any time variables involved, so it's been factored outside the integral. It's treated like a regular constant. On the right, we're integrating 1 divided by the difference of this terminal velocity in v from the initial downward velocity of v sub 0, or v naught, however you want to say that, to the upper limit, which is the expression that we want to eventually solve for, v sub y, as a function of time. Before, I said I would explain on this slide why I used t prime as an integration variable. So let me do that now real quick. Basically, we're breaking a math rule if we have the same integration variable that's used in the integration limits. For example, it doesn't make any mathematical sense if we would integrate from 0 to t using dt. In that kind of situation, something has to change. And since we're expecting t in our final answer, it means that it's a better choice to leave t as the top integration limit and then switch dt to something else instead. And the simplest choice is to just stick a prime on t. Now, I know for some people watching this, it might seem like a ridiculous thing to kind of get up in arms over, but the mathematicians are right when they say that it doesn't make sense if you set up the integral incorrectly. So that's why we're doing it this way, the right way. If I'm going to explain how this problem is done, I don't want to pass along any bad habits that will get you in trouble in any other math course. So in any case, let's move on to integrating the left side first, which is really easy because all we're doing is integrating 1, which I've omitted. When you integrate 1, you get your integration variable back, which is just t prime, and we will evaluate that at the endpoints of 0 and t, which looks like this. There's nothing too hard there. We'll end up with k over m times t minus 0. So it's just that on the left-hand side. On the other side, on the right side, I'd like to introduce a helpful reminder. If you're familiar with some calculus already, you may have seen that the integral of 1 over x, or 1 over v in this situation, well, that results in the natural logarithm of v, plus some constant if we don't include endpoints, if we want to show the complete answer. But we have something a little bit more complicated here than that. It's a difference involving v. It's not just v by itself. Well, that's okay, though, because the result isn't too different. Instead of the natural logarithm of v, we end up with the natural logarithm of the difference. And then we have to slap a negative out in front of that. Well, that's not too bad, right? It's pretty similar, right? They're both logarithms. Instead of v, it's a difference, and then it's negative. Okay, cool. Let's go ahead and finish up the right-hand side so that we can continue. Like with the left-hand side and t, we're going to take this integral result and evaluate at the endpoints that we had previously, like this. But first, take a look at the left-hand side. Our starting equation from the problem description, it didn't have k over m times t in it. It had negative k over m times t. And our answer is going to be very similar to that. So we need to find a way to switch things up and incorporate that negative. We can deal with that by multiplying both sides of this current equation by -1. Let's finish things up on the right. Here's another helpful reminder. The difference of two logarithms can be rewritten as a single logarithmic expression, one that just involves the first term divided by the second. So let's put our logarithms in the same form, like this. Notice that the variable that we want to solve for, v sub y as a function of time, well, that's now in the expression. It's no longer hanging out in a limit somewhere. The only problem is it's buried inside this natural logarithm, like some nested Russian doll. We need to get that out of there. How are we going to do that? Well, we'll take the exponential of both sides on a fresh slide. Here, both sides of the expression have been placed in the exponent of the exponential function. It looks like this thing is way worse than what we were just previously dealing with, but remember that the exponential function and the logarithmic functions are inverse operations of one another. So that means they're going to kill each other off, and we'll be left with just what's in the parentheses on the right-hand side. So that's great. Super helpful. If we want to isolate this variable here, our first step is to multiply both sides of this equation here by the difference in the denominator of the right-hand side, like that. Following that step, let's exchange all this stuff on the left-hand side with our variable that we want on the right. So this will come over here and become positive, and all of this will come over here and become negative, like this. We are so close to the answer to part A, but there's still a little cleanup that we have to do. I'm going to distribute this exponential part at the end of the parentheses to the difference inside to get the full expression, like this. And why did we do that? Well, take a look at these first and second terms here. They both have the terminal velocity hanging around in them. So let's just go ahead and factor that out. I'll bring that to a fresh slide, do that, and now, 6 parts later, we are finally done with part A. It's been quite a journey, huh? Let's not forget about the rest of the problem, though. For part B, we're going to take this equation and graph what the behavior looks like when the initial downward velocity, okay, v sub 0 or v naught, when that is lower than the terminal velocity. To do that, let's use another kind of trick. We weren't provided with any values for v sub t or v sub 0, and we weren't provided with k or m either. So instead, we're going to make some ourselves. Let's set the beginning velocity to something simple, like 0.5. Choose whatever you want, but I would recommend setting everything else to 1 for the sake of simplicity. And this is totally okay, because all we want is the shape of the graph. If you change these values, the overall shape will remain the same. Okay? So we're not breaking anything by doing this. If we incorporate those numbers, here's what we're going to be graphing at the bottom. That doesn't look so intimidating anymore, right? To graph these, I'll show you what I did using the capabilities on Desmos.com. Here you can see the equation that I entered on the left, and that worked just fine. Instead of x, I did t. And what does this graph tell us? Well, at the beginning time, t is equal to 0, our object is falling with the initial downward velocity of v sub 0 equals 0.5 that we chose. Okay? And then after falling for a couple of seconds, it comes closer and closer and closer to the terminal velocity of 1, and it stays there, just like we would expect. Because remember, we said once you hit terminal velocity, you don't accelerate anymore. and your speed should remain the same. And that is reflected in our graph. So, cool. That is all that part B wanted us to do. For part C, we're going to switch things around. It's still the same equation up at the top, but now I'm going to set the initial downward velocity to something larger than 1. Okay, I picked 1.5. Use whatever you like, as long as you meet that requirement. How does this change the look of the graph? Well, it appears that the shape is flipped. Instead of speeding up to reach the terminal velocity, this time we start at t is equal to 0 at a faster speed, and then we gradually slow down to reach terminal velocity. Interesting. One case left. This time, let's set everything equal to 1. Can we predict what the graph will look like before we even pull up the Desmos picture? Well, I would say yes, we can. Take a look at our equation down here. If we're going to add this second term, which is negative, with this last term, which is positive, well, they're the same thing, and they're going to cancel each other out. What are we left with? Well, just 1. This means our graph should be a completely flat line at y is equal to 1. Is that what we get? Well, it is, yes. This means that if you fall at the same speed as the terminal velocity, nothing will change. You will continue to fall at that rate without speeding up or slowing down, which is completely in line with everything I've been saying. All the parts are now done. That's all, folks. I hope this wasn't too agonizing. Thank you for watching, and I hope you all have a great week. Take care.